In the previous video, we looked at rational functions with quadratic denominators, and in part 3, we are looking at partial fractions. But before we get into partial fractions, let's just go over what we mean by rational functions. And so let's go back to the definition of a rational number, which is any number that can be expressed in the form P on Q, where P and Q must be integers. We also know when we're dealing with fractions like this, that if we have P is greater than Q, so the number on the numerator is greater than the number on the denominator, we have an improper fraction. And if the numerator P is smaller than the denominator Q, we have a proper fraction. Okay, so some very basic revision here, but now let's link this to rational functions. So instead of a rational number, if we have a rational function, this is some function that is f of x over g of x, where f of x and g of x are polynomials. And then the same rules apply down here. If f of x is greater than g of x, then we have an improper function. And if f of x is less than g of x, we have a proper function. Now, when we start with an improper function, where we have a higher degree polynomial on top, we can break this down. And likewise with a proper function, we can decompose, that's the technical name, we can decompose these into partial fractions. So partial fractions are the main focus of this video, so most of the ones we'll be looking at, the function on the top will be less than the function on the bottom in terms of the degree, but we are going to start with an improper question first of all. So our first example is an improper function. So example 1, we have the integral of x cubed over x squared plus 1. So we have a cubic or a degree 3 polynomial on the top and a quadratic or a degree 2 polynomial on the bottom. So this is improper. And like I just said before, this does not involve partial fractions, which are the focus of this video, but it's still a really good question. One of the reasons it's good is that it links to an example we did in the previous video, which was this one. And if you recall, the way we solved this was we thought, wouldn't it be nice if we had x squared plus 1 on the top? Because then we'll have x squared plus 1 over x squared plus 1. And so we had to add in a 1, but then also subtract a 1 at the same time. So go back and watch that if you need to. But we are going to use a similar kind of thinking to solve this one. So wouldn't it be nice if we had x squared plus 1 on our numerator? We don't, of course, but wouldn't that be good? Well, what do we have? We have a cubic function. So how can we turn this into a cubic function? Well, because it's a quadratic, we could multiply by x. So we have x cubed plus x. Right, so if we add an x in here, then, and it looks like this, then we can factorize and get this. But we can't just go and add an x in, as that would change the question. So we also need to subtract an x as well. So our integral can instead be written as x cubed plus x minus x all over x squared plus 1. The reason we did this was so that we get an x squared plus 1 term. So going to split this fraction now, and at the same time, this x cubed plus x, remember, that is the same as x outside of x squared plus 1. So there's the first fraction, and then we're going to subtract the second fraction, which is x over x squared plus 1. Focusing on the first fraction, this cancels really nicely. The x squared plus 1 and the x squared plus 1 cancel out to leave us simply with x, and then we have this term. Now, hopefully we can use our skills from last lesson and recognize, okay, we have a linear function of x over a quadratic function of x. So this is looking like the natural log rule. However, the derivative of x squared plus 1 is 2x, and we just have x. So what we would rather see is a 2x over x squared plus 1. And so to compensate, we'll multiply by a half. Okay, we'll put that in there. And now we are ready to go and integrate. So first of all, the integral of x, that is x squared on 2. And then we need to take away the integral of this guy. So we have our constant half, that's fine. And this now we can apply the natural log rule. And there we have it. Okay, so once again, just going over that technique of being a little bit creative with our numerator. Right, we added in an x and we took it away as well, so nothing really changed, but we did this so that we could introduce an x squared plus 1 term, which then cancelled. So this is an improper function, so to speak, that can be broken down into just a polynomial and a proper rational function here. Let's now focus on some examples that involve proper rational functions, and let's break these down into simpler fractions, and this is what partial fractions is all about. So example 2, 1 over x squared plus x minus 2. Now the reason we're doing this example is because you might remember, maybe not, but at the start of last video we looked at this quadratic and we said, can we factorize this? And the answer is yes. If we factorize this quadratic, we get 1 over, well, we need factors of -2, so either -2 and 1 or -1 and 2, but we want +1. Okay, so x minus 1, x plus 2. That's what we would get when we factorize this thing. And in the last video, we didn't deal with these. We only dealt with perfect squares. What are we going to do here? Right, as it stands, we don't have the skills to integrate this. So we want to decompose it into some simpler fractions. And so what we are going to do, we'll just separately go off and focus on this, is say, all right, there's some fraction. I don't know what its numerator is, so I'm just going to give that the letter A. But I'm going to say that its denominator is just x minus 1. And when I add it with another fraction, once again where I don't know the numerator, but its denominator is x plus 2, I know I can make these work. Right? Think about taking separate fractions and adding them together. We know that in order to add or subtract fractions, the denominators must be the same. And so in this case, noting that the denominators are different, we would set about trying to make them the same. And one way that we can always do that is to just multiply the denominators together. And that's what we have over here originally, x minus 1 multiplied by x plus 2. Okay, so once we set up our question like this, we need to go about solving a and b. And so the first step is to take this original denominator and multiply everything by that. And so what effect will that have? Well, over on the left-hand side, when we multiply by what's on the denominator, it'll just cancel to leave us with the numerator of 1. Now let's focus on each fraction on the right-hand side. The x minus 1's will cancel, and so we'll be left with a outside of x plus 2. And then in our second fraction, the same kind of thing will happen. We'll be left with b, but now the x plus 2 values will cancel, and so we've got b outside of x minus 1. And this kind of makes sense if you think about cross-multiplying, if you were aiming to combine these fractions into 1. Now there still might be a little bit of an issue though in your mind if you think, hang on, we're trying to work out a and b. That's 2 unknowns, and we only have the one equation. So what we need to do is to equate coefficients. Remember that if we have some equation like this, the only way that ax squared plus bx plus c can be equal to 2x squared minus x plus 3 is if we equate coefficients. So the coefficients of x squared, a, and 2 must be equal. The coefficients of x, b, and negative 1, so b equals negative 1, they must be equal. And finally, the coefficients, well, of x to the 0, the constants, they must be equal. So c equals 3. So equating coefficients is the way in which we can work out multiple unknowns with just one equation. So let's do that with our question. So expanding on the right, we get ax plus 2a, and then in our second expansion we get bx minus b. And if we group our coefficients of x together, we get a and b multiplied by x, and our constant comes from 2a minus b. And so comparing that to the left-hand side, where we have a constant of 1 and we have a coefficient of x of 0, we can now draw up some simultaneous equations. So let's focus on the coefficient of x. From this, we can see that our first equation is a plus b must equal 0. This is equation 1. Our second bit of information comes from the constant. 1 must be equivalent to 2a minus b. 2a minus b must be equal to 1. And so this is our second of our simultaneous equations. And so we can solve these. Right? We have the skills to solve simultaneous equations. There's different ways to do it, of course. One such way is to notice that we have a positive b and a negative b. So if we take both of our equations and add them together, well, that means b and negative b will cancel out. And so we get a plus 2a is 3a, and 0 plus 1 is 1. Therefore, a must be a third. And since we know that a is a third, then we can see b must be negative 1/3. And so we have figured out our values of a and b. Now, while that wasn't hard, there is another sort of shortcut way to figure these out a little bit quicker. And it involves looking back at our very first line back here. Because this must be true for any value of x, right? So x is our general variable throughout the question, we're dealing with functions of x, so this will always be true regardless of the value of x. It means we can actually pick a value of x that might suit us. So if you look back up here, we notice that if we choose x to be 1 or x to be -2, then these disappear. So let's just pick one of those. Let's say we say x is equal to 1. If x is equal to 1, then this whole expression disappears because 1 minus 1 is 0, and 0 times b is 0. And so what do we get? 1 on the left-hand side is equal to a outside of 1 plus 2. In other words, 1 is equal to 3a. And so we've come up with that really quickly. And we can work out that a must be a third. And likewise, if we choose -2, if x is equal to -2, then this disappears, right? -2 plus 2 is 0, so this whole term here disappears, and we have that 1 is equal to b times -2 minus 1, or -3 lots of b gives 1, and so likewise we can come up with b equals minus a third. So that's like a little hack, a little shortcut way to do it. So you don't necessarily have to equate coefficients, but that definitely works. And in this case, it wasn't particularly hard to go through our simultaneous equations approach, but this is really nice as well to do that. So we will try and look out for that with more examples as we go. But let's get back to actually completing our integral, because we now know that a is a third and b is minus a third. And remember, if we go back to how we set up our question initially, we had taken our initial fraction and we had said that it can be expressed in this form, and we've just found out that a is 1/3 and b is minus 1/3. So I might put a minus here. And so simplifying this a little bit by dragging out 1/3 as a common factor, we can express our original fraction as two simpler partial fractions. And both of these we can integrate. So let's go ahead and integrate this guy. So our initial integral could be factorized, and then we saw that this fraction could be decomposed into these guys. And when we look at these two fractions individually, we notice that we can use the natural log. So we get 1/3, we'll keep that out the front. This one becomes the natural log of the absolute value of x minus 1. And then we need to take away the natural log of x plus 2. There's our plus c because it's indefinite. And yeah, I mean, we could actually, if we want to be a bit tricky, we could use log laws to combine these. So when we have the natural log of sum a minus the natural log of sum b, this becomes a fraction a on b. So that looks nice as well. And so there we go. We have solved what started out as quite a tricky proper function, but we were able to decompose it into simpler partial fractions. So let's go ahead and do another example, this time with three values a, b, and c that we're going to find. So for this third example, we are not going to worry about actually integrating. We're just going to focus on our partial fraction skills. So we're told that if 6 over x minus 1 times x plus 1 times x plus 2 is equal to sum a over x minus 1 plus sum b over x plus 1 plus sum c over x plus 2, let's find the values of a, b, and c. Because once we do that, we can rewrite this initial fraction that would be hard to integrate as the sum of these three individual, simpler partial fractions, which we then could integrate. So what are we going to do? Well, remember, if we multiply by everything that is on this denominator, then we get a little bit of cancelling. We get rid of our fractions. So let's go ahead and do that. On the left-hand side, we will just be left with 6. And now on the right-hand side, we have a. The x minus 1s will cancel, but we still have x plus 1, x plus 2. Then we move on to our second fraction that involves b, and here the x plus 1s will cancel, meaning that we are left with x minus 1 and x plus 2. And finally, our third fraction with c, where the x plus 2s cancel. So, a little bit longer this one, and we can see that we have quadratics when we expand these. So we're going to need to consider 0x squared and 0x with our 6. So I might just add them in here. 0x squared plus 0x plus 6, right, when we go ahead and equate coefficients. So let's quickly expand these. We have x squared plus 1x plus 2x is plus 3x and a constant of 2. Then here we have another x squared minus x plus 2x gives us plus x, and a negative 2 is the constant. And our final quadratic here we have, well, it's a difference of 2 squares, isn't it? So it's just x squared minus 1. That's nice. And now let's write it so that we group all of our x squared terms together. So that's simply a plus b plus c. Okay, so we have a plus b plus c, lots of x squared. Now let's focus on the terms of x. So just got to be a little bit more careful, but we're going to have 3a times x, so 3a. We're going to have b times x, so b. And, well, that's it. There's no, c doesn't get multiplied by an x term, so that's it there. And finally, our constant term, 2 times a minus 2 times b and minus 1 lot of c. That's our constant. And so we can compare each of those with what we have over here. A plus b plus c must be 0. 3a plus b must be 0. And finally, our constant term of 6 must be equal to this guy, 2a minus 2b minus c. So let's write each of those out as separate equations. So equation 1, a plus b plus c equals 0. Equation 2, 3a plus b is equal to 0. And then our third equation, 2a minus 2b minus c equals 6. And so now it's time to solve. Now, looking at these three, one thing that really jumps out to me is that this middle equation only involves a and b. And so we can very easily change this around so that we get b as a function of a. So this can be now our fourth equation, and we can use this and substitute it into our other equations to completely eliminate b. So let's go ahead and do that. So first of all, let's sub this equation into equation 1. So we get a plus b, but that's now minus 3a. So we get a plus minus 3a, or negative 2a, plus c equals 0. So that's another new equation that we get. We'll call this equation 5. And we can also sub equation 4 into this other one. So 2a, this one I'll write out, 2a minus 2 lots of b, but b is minus 3a, minus c equals 6. And so simplifying, well, negative 2 times negative 3, that gives us positive 6. And so we get 2a plus 6a is 8a, minus c equals 6. And so this is another new equation that we've come up with, our 6th now. Now if we compare equations 5 and 6, these latest two that we've come up with, they just involve a and c, both of them. And what's good is that it's one lot of c and minus one lot of c. So we can simply add them together and the c's will disappear. So minus 2a plus 8a gives us 6a, plus c minus c, that disappears, and 0 plus 6 gives us 6. And so we've now worked out what a is. A must be 1. Once we've got one of our variables, everything else falls into place really nicely. We can see back here that b is just minus 3 times a. So very easy to see that b must be minus 3. Okay, so that's from the fourth equation. And also, if we look at the fifth equation that involves a and c, we can see that since a is 1, that's negative 2, and so c must be 2. Okay, so that's from looking at the fifth equation. So, a bit of work to figure out our first variable, but once we've got it, super easy. And so now that we've figured out the values of a, b, and c, we can rewrite that initial fraction, right? Which helps us when we're integrating. So the initial fraction, which was this guy, can be rewritten as a, or 1 over x minus 1, plus b, oh well, that's minus 3, isn't it? So minus 3 over x plus 1, and plus c, which is 2 over x plus 2.